I'm Frank, this is Payman, this is DS340, it's fall 2020, and we're going to talk about Kernel Trick today mostly. Hang on to your hats. Last time we talked about basically convolutional feature banks and feature engineering such that you could draw spatial information from regions by basically combining the outputs in various ways of convolutional filters. And we talked about this dense segmentation problem. I tried to label every voxel in some volume as being, tumor or not. And it turns out that with the feature banks that we talked about and operations on them, you can solve this problem fairly well, and the best performance was attained with linear classifiers of the type we've been talking about: support vector machines, logistic regression, provided that you did feature selection or use some sort of regularization. Fine. Today, we're going to do something more fun. I mean, that's fun, but this is fun. Okay, so Payman, can we use linear models for data that's not close to separable, like what we have here? So we have two features, and a bunch of data points and labels.
Not really, unless we change the way we represent the data.
Exactly. Okay. So exactly. So we can't really draw a hyperplane in this space, right? There's no linear separation of this data in the original feature space, right? But we know about changes of bases, and if we think hard enough and we design a good change of basis, right? What would we do? We'd try to build something that looks a little bit circular. So maybe if we actually made a change of basis that included all of these features, which sort of look like, the things that you would use to indicate distance away from the origin, right? And this was Z1, this was Z2, and this is Z3, then maybe, again, this being Z1, Z2, Z3, maybe actually we can find a hyperplane in this higher dimensional space. Yeah, polar coordinates, decision tree. Yeah, but we're talking about can we use linear models? So that's the versus the decision tree thing, right? And can we do it for data that's not close to separable? Okay, so and the answer is, roughly speaking, yes. If you feature engineer some very, very good change of basis, right, that's sufficiently complex to actually separate the data. Okay. Now, something that I've said several times during the course, and I just want to make sure that it's super clear. If you basically set this equal to 0, which is for linear classification models, the boundary at which the class changes, right? Or at least that's how we decide which is one class or the other. If we look at the solution to an equation like this, then in the original feature space, where we're now looking at in the original feature space X, the solution boundary looks like this. Okay, so the point is you can when you expand your features, so what's the point? We have some data. We don't know what its decision surfaces look like because it's in some high dimensional space. This is just a two-dimensional example, but we get some data. We don't know how to separate it. We have the intuition that if we project this into some higher dimensional feature space, we might be able to linearly separate it. We're probably never going to be able to go back and look at this thing, but the intuition is that when the decision surface in the original space can be much, much more complex as a result of having projected into this higher dimensional space and learned separating hyperplane there. Okay, fine. Okay, so this is all set up for what's going to come. Before we go there, what we want to do is think back to when we were building polynomial basis functions. Okay, so when we quote unquote fit polynomials with one feature, we did a basis expansion to zi equals 1 xi squared, whatever, right? And then we fit a model like that, right? That's what we did, right?
Yeah.
So we took our original theta, then we built, xi squared, xi, excuse me, 0, xi to 0, xi to the 1, and xi to the 2. Okay, right? So the first question is, what if we have extra features here? How do we do this? Right, so if d is not equal 1, how do we build such a polynomial basis? And we had some, we talked about this a little bit, but let's just like refresh ourselves, right? How do we do this, right? So if we want to build, so here now we have d equals 2, and we want to build a polynomial basis. And we want to build a polynomial basis of order 2. Well, what do we do? Well, we have our, bias term, our intercept term. The original dimensions, xi1, xi2, right? So that's just copying these values over, right? And then we have the squared terms. And we have what I'll call the cross product terms. Okay. So this is a complete polynomial basis for original feature space dimension d equals 2 and polynomial order 2. Okay. If the original feature space is 4-dimensional and we choose a 3rd degree polynomial, right, the polynomial basis would include a bunch of terms, right? If you actually went out and selected all the terms, right? It would include all the bias variable on all of the individual terms. It would include all the squared terms, all the cubed terms. It would have all the two-way interactions. It would have all the cubic interactions, so on and so forth, okay? So the point is that if we have relatively high dimensional features to begin with, and we choose a relatively high dimensional polynomial, then the number of features in Zi is big, okay? All right, cool. Now that's cool. This is good and bad, right? It means it's a more flexible model, maybe overfits, but we can regularize, so on and so forth. So it's like we're really thinking about the case where we really don't actually know that much about the data, and we want to have a generic method that allows us to build very large feature spaces that then we can select amongst so that we can have expressive models that are still powerful and don't overfit via regularization, okay? If we go to a 5th order polynomial, I hope Payman's still alive, we have order d to the 5th quintic terms. Okay, so tons and tons and tons of terms in our basis, right? And if you think about it for a little while and do the combinatorics, basically for a large d and a large p, storing or computing a polynomial basis is intractable. Okay, the expanded basis feature dimension is order d to the p. That's how many in dimension. Like that's how many columns your new basis would have. And it's not going to fit in memory. You're not going to be able to compute with it, so on and so forth. It would be really cool if you could, because this is an incredibly powerful basis, right? Like if you do feature selection amongst this basis, you're going to have like every possible, like a lot of features, an exponential number of features. Cool, right? Now, how could you deal with that? I mean, you could do some sort of forward selection thing, maybe being smart about which terms of the polynomial, like so that you don't like, double count polynomial. But basically, you do some sort of fancy forward selection thing. That's one thing you could do, but that's going to be problematic for the same reasons that all of the model selection things are problematic. But today is about something really cool, right? Which is called the kernel trick, okay? And this allows you to compute with all of the features. Okay, so Shaunak, there's a good question which Payman didn't bring to my attention because he's like too busy making sure that he has the right number of buttons buttoned or something. I don't know. So more features doesn't always mean a better result. Right. Okay. Correct. That's right. So you can overfit and so on and so forth. But if you do some sort of regularization, right? So in other words, let's pretend, and we're not going to be able to do L1 regularization with this or L0 regularization, but let's pretend like you don't know anything about the problem, right? You're not a feature engineer. What do you want then? You want to actually have as many features as you possibly can have to select amongst, right? And then probably some of those features are going to actually be useful, particularly if you use some sort of regularization technique to, pick amongst them, even if it's L2 regularization, right? Okay. So in that sense, if you don't know how to design the feature set, right, or worse yet, you actually need a very large number of features in order to draw a decision boundary that's complex enough. Yeah, so basically that's exactly right. So the comment is we'll have way more features, right? Then we regularize appropriately to avoid overfitting, right? Okay. And to foreshadow, we're even going to be able to deal with an infinite number of features, okay? Which is pretty cool. Okay. So again, I've already said that we're going to restrict ourselves to L2 regularized linear models in this discussion, and it should be relatively clear why that's the case if you look at the maths later. That's coming. Okay, so I think we've got ourselves set up fairly well at this point, right? For the next thing that we need to do is we have to remember that when we set up the L2 regularized least squares objective, right? We had our square square penalty on the residuals or on the, yeah, that's fine. And then the L2 regularization on the parameters, right? And we're operating in basis Z with parameters V, okay? So we're gonna think about the expanded feature set for a second. And then we showed that that a minimizer was given by this equation. This equation should be very comfortable for all of you at this point. That's nothing terribly surprising. Just remember that this is K by K rather than D by D. So fine. You could solve a linear system instead of taking the inverse, but we're going to just think about it this way for the time being. With a little bit of linear algebra, it's pretty straightforward to move between these two, okay? So you can write the solution or derive that V is equivalent, like it's exactly the same, right? They're exactly the same. Like a solution to the least squares problem also looks like this, where this matrix now is n by n. Okay, so you can do the algebra yourself. So I'm not going to do the algebra, right? The point is that they're equivalent, and it's just a reshuffling of the matrices and their inversions and that sort of stuff. And inside there is this n by n term. Okay. Now, if n happens to be smaller than k, then solving for your linear solving the least L2 regularized least squares objective is faster if n is much less than k, okay? Because all of the complexity, so this is an n by n matrix, you have to invert that, that's n cubed, forming the other one is n squared k, right? So this is smaller than this if n is much smaller than k. Okay, now, how could that be, right? Why would we do this? Again, just think already, we've already talked about an exponential number of features. So k could be really large, right? In fact, we already know that if we compute with a complete polynomial basis for large original feature dimension d and some reasonable order p, then k is exponentially large. Okay, So even though n might be smaller than k, even this term might be too much. Okay? But there's two things to think about here. One is, right, if n is small, then we're okay relative to k in terms of the matrix inversion bit, that sort of thing. The other bit is, you know, this k term is quite large, so we're going to attack both of them. Okay. I'm going to take this right here and just write it on the next slide. So that is the other normal equations, which again you can derive yourself, and just trust me that this is the case. We have that our model parameters are v, right, equals this thing. Okay. And these are our, you know, feature vector, you know, the expanded basis feature vectors, basically, right, of the inputs. Let's think about how we produce predictions, test predictions, right? So if we have test data x tilde in our notation, we can use our basis expansion to form z tilde, right? And using z tilde and our learned parameter v, right? That's how we make our prediction y hat, right? Nothing new here. If we plug in the definition of v here, then we're going to recognize something, and this is basically the beginning of the kernel trick. Okay. What we're going to recognize or identify, we're going to call this z transpose thing a matrix K, and we're going to call this z twiddle times z transpose matrix another matrix called K twiddle. And by defining those things this way, then we can write down our prediction in terms of these matrices K tilde and K. And it shouldn't be clear why we're doing this yet. Okay. We know that this inner bit is n by n. We know this is n by 1. And we know that K tilde is t by n because we have t predictions that we want to make. And if you just look at the dimensions of this, it'll be clear that it's t by n. So I haven't told you how to get them, but if you have k, somebody handed you k and k tilde, then you actually don't need z and z tilde in order to actually make your predictions, right? Fair? Okay. Okay. Well, cool. The kernel trick is the name basically given to methods that allow us to efficiently compute k and k tilde without ever forming z and z tilde. We're just never ever going to form them. Okay. And the computation of k and k tilde will actually be efficient. Okay. In particular, constructing this will be efficient. Okay, cool. Some nomenclature. The matrix K equals Z times Z transpose is called the Gram matrix K. Okay. All right. And let's think about what K is made up of, and this is really important. So K is made up of. Well, how do we fill this in? Well, we take this vector and this vector. So this is just the basis vectors and the expanded basis, right? Take a dot product of those, right? Then we take a dot product of this one with this one, so on and so forth, okay? So every row and every column of K is formed of the inner product of expanded basis vectors Zi, Zj. Okay. So the kernel matrix contains the dot product between all training examples, right? And this is a little bit like how we constructed the matrix Z when we were doing radial basis functions, but here we use a dot product instead of some sort of distance. And there's a little bit of a relationship between the two of them, but we'll get to that in a little bit. Okay, fine. Okay. K tilde is similar. It's just Z tilde times Z transpose, right? So we talked about the dimension of this before. So we have this matrix Z tilde is T by N, and this is N by N. So the ultimate matrix is T by N. And again, K tilde consists of inner products between the basis expansion for a test input and the basis expansion for a training input. Okay, so these are just all dot products, inner products, right? So here it comes. This is the magic. This is the fun part, right? So let's pretend. Let's play this. Let's pretend that there's this magical function called the kernel function, right? And notably, this is really important to note, and this is this is probably the one benefit of attending lectures. You get to see these things, and you don't have to read it and find it 10 times later, you know, like much later. The kernel function takes as input the original feature vectors for I and J, data items I and J. Okay. And the value it produces, the thing that it computes, is Zi transpose Zj. Okay. Okay. So I want to be as clear as I can be here, right? We're saying that there is some magic function, this kernel function, which will give us the same value as this inner product. Okay, so it's not, you know, obviously this function doesn't have Zi's as an input, so maybe we should say these are equivalent, right? The value of the kernel function, yeah, exactly. Okay. Xi and Xj are both vectors. That's right. Okay. So basically, what I'm saying is that we're going to have some crazy function, kernel function K, that when you give it the original feature vectors, it's going to produce a value which is the same as taking the dot product between the vectors in the expanded feature space. Okay. In the expanded basis. Yeah. Okay. All right. Before we talk about exactly where this magic function comes from or how it could possibly exist or examples of it or something like that, let's just make sure that we're clear about the fact that to do, for instance, linear regression, you really only need to know K and K tilde, right? So we established this, but basically the way we started talking about this is we say, okay, we do our basis expansion from Xi to Xj, from Xj to Zj, right? We use those to compute Zi transpose Zj, right? And then we stick those in our gram matrix K. That's the original way we went about this. This is what we said is going to happen. Now we know K, we're good, right? Final result is this n by n matrix. Doesn't matter how large the original feature space or the expanded feature space is. The point is, we are not going to do this, okay? We're going to assume that we have this magic kernel function that allows us to directly compute the entries of this K, this gram matrix, from the X's, not the Z's, okay? And ideally, computing this entry will be cheap, okay? Hopefully the whoa comment still stands, okay? Right? So just to keep on this pedantic path, when we're doing linear regression, not kernelized, right? We form Z from X We compute our model parameters. We basically minimize the normal equations, right? Find a minimizer of the normal equations. When we test, we form a basis z tilde from x tilde. We compute our predictions using our k by one dimensional parameter and the basis expanded vectors for the test data. Kernel regression, we do the following. We form the inner products in K directly from X. We compute this U quantity, right? Right? Our parameters, as it were. Then we form the inner products in K tilde from X and X tilde directly. And then we compute our predictions by multiplying K tilde by U. Okay. The point is, again, we never need to compute any of these z's. Everything that we need to know about that expanded feature space is in K, if we have such a magic kernel function. Okay, so let's talk about this magic function. Okay, let's take a really stupid version of this function, a very simple, trivial version. So let's say we have two examples, xi and xj.
So there is no regularization for kernel regression?
Quite to the contrary, it only applies when we are doing L2 regularization. It's baked in. Exactly. So let's say that we have two examples, xi and xj, and we have our standard. Let's take a standard linear basis, okay? Which means that our feature expansion is not an expansion that literally is just copying the features over. Okay, so the inner product between zi and zj. Well, we can definitely compute that using some kernel function k by just taking an inner product of xi and xj. Right? That's obvious. it's basically a no-op, right? Gets a little more interesting when we start thinking about more interesting feature transformations. Okay, so let's say we have the same two data points, two-dimensional data points, two-dimensional data set, d equals 2, right? We have xi and xj, and let's consider a particular, this is chosen very specifically, degree 2 basis. Okay, so we're going to take xi and we're going to transform it into zj, right? And we're going to do that by squaring xi1, squaring xi2, and root 2, blah, 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 blah. Okay, fine. In this case, we can show that there exists a kernel function that operates on xi and xj directly that computes the value of the inner product between zi and zj. And I will assert that that kernel function is simply xi transpose xj, or the inner product of xi xj, the value of that squared. Okay. So these two values are the same. Okay. And we can do this by expanding out zi transpose zj. So multiply this by this, multiply, this by this. So we're just taking the dot product, right? Simplify it a little bit, get rid of the root 2, and multiply through the root 2s, right? If you complete the square, go this way, it's really easy to see. Got this squared, and the cross product term, right? If you squint at this just a second, you'll see that this inner thing here, this inner thing right here, is just the inner product between these vectors, right? It's xi1 times xj1 plus xi2 times xj2. Okay.
Will every basis transformation have an equivalent kernel function?
Every basis transformation have an equivalent kernel function. There are basis transformations for which kernel functions have not been found. It is not the case that every basis transformation will necessarily have an equivalent kernel function. Finding the kernel function in that direction is insanely difficult and often not possible. Yeah. But that's okay, because if you have an infinite number of features, maybe it's not so important. Okay. So, okay. So let's just make sure that everybody's on board with this, right? This kernel function computes this value with this basis expansion. Lots of scribbling. Hopefully it still makes sense. So we don't need to actually instantiate these expanded basis vectors to compute their inner product. Okay. What if we add a bias in linear terms to this degree 2 basis, right? So we say, okay, this is the basis we want to compute in, and now we can, you know, what we can show is that if you compute the following kernel function, so 1 plus the inner product of the original feature vectors squared, adding this 1 adds all of these terms to your basis. Okay. So you can do this by, you know, taking this computation, the 1 plus xix inner product xi xj, expand it out, expand out these into their constituent parts. Same thing with this, and then see that this is indeed the inner product of these vectors z. Okay. So this kernel function computes all the complete degree 2 basis via this right here. And we won't go into the algebra, too much of the algebraic basis. We're not going to derive this, but you can work it out that you know, if you want the monomials, basically you use a form like this. So this is all degree 4 monomials. You just manually work it out if you want to. It's horrible. And it's basically equivalent to using a z with weighted versions of all of the terms like this. If we want the lower order terms, then you add the 1. And in general, the general degree p polynomial kernel function looks like this. Okay, and this works for any number of features d.
Multinomial theorem.
Weird Pascal triangle math. Yeah, exactly. The point, though, is that when we compute this, right, this only involves an inner product in the original feature space. So this is an order d time operation. So this is, you know, d multiplications plus 1 addition plus 1 exponentiation, right? So the cost of computing 1 entry is just order d, right? Instead of order d to the p, right? So that means we've attacked everything. So now we've made the solution to the kernelized least squares problem basically good by using you know, matrix inversion of size n, so an n-cubed operation, but then the ODP term also goes to OD, like we were hoping for. So how do we actually compute with these? It should be pretty straightforward, right? So the ijth entry of the Gram matrix K is just this. You just evaluate your kernel function on input feature vectors I and j, so xij. Then your test data looks like this. It's 1, plus, it's the kernel function applied to the test example and the training example. And you make predictions using the equations that we've already provided. So here are the labels, and then, here's the kernelized solution, right? Now, the point is also, just to be clear, that you can sort of amortize this cost. You don't have to recompute that. That's just, you can just compute that once, and that's you. So the point now is that the training cost of this is OND squared plus n cubed, right? Despite the fact that we're using an exponential number of features. And here we're talking about the polynomial basis of degree p, right? In fact, this is going to be true for whatever kernel function we use, because it's just that's just functions of dot products in the original space. And the testing cost is also low. We only have to form k total, which is O and dt. Right? The most common kernel that people use is the Gaussian radio basis function kernel. And it's the same formula and has some similar behavior to the radio basis function basis, but it's not equivalent, right? So before we used radio basis functions as the basis, but here we're using them as an inner product. And the fun thing about this is that the basis that this corresponds to is infinite dimensional, right? So with original feature space dimension 1 and sigma equal to 1, you can work it out. It's in the bonus slides that the basis in which you're computing is infinite dimensional. It looks like so it has all polynomial orders and term in front. Okay.
Taylor expansion.
Looks a lot like a Taylor expansion. It doesn't, except for that thing right there. Yeah. So this is how we represent infinite features. Yeah, basically. So if you do kernelized least squares regression or any of the kernelized versions of the other things that other linear models that we've talked about, SVMs, logistic regression, and so on and so forth, if you use a kernel like this, then indeed you are computing in an infinite dimensional feature space, right? Which means that your model is pretty darn expressive, right? So it's this nice balance of what's a real world example of something with infinite features. The world, indeed. Can you do autoregressions this way? Well, autoregressions are just regressions, so yes. Cool. I think, Sean, to be less snarky in response to your question about what's a real world example of something with infinite features, again, I think the more useful way of thinking about this is if you want to build a generic model that's powerful, what you really don't want to do is feature engineering, right? You really would like to use an incredibly large basis vector set, like you'd like to use an incredibly expressive basis, and then select the features out of that, right? So, is this the correct basis? There's still a model selection problem, like do you use a polynomial or kernel? Do you use an RBF kernel? Do you use some combination of them? Do you use a Matern 5/3 kernel? Whatever, there's a whole bunch of kernels that you can use. You can construct new kernels, so on and so forth. But the point is that you get a very, very flexible basis that you can use, that is automatically regularized in some sense, and generally leads to very, very good generic results. How does this relate to the kernels we talked about in the convolution lectures? Similar sampling. So I shouldn't have used the word kernel there. This is a different deal. This is a different beast. Okay, so we talked about a motivation for this lecture. Sometimes I skip over them pretty quickly, but if you were a geotechnical engineer or something like that, and you wanted to estimate where high density or high mineral concentration regions of some space, some like location on Earth. What you could do is you could go off and you could, you know, make a bunch of boreholes and pull up samples and, you know, do material assays and figure out how much gold is in those particular locations by volume, something like that. And then drill holes, measure gold content. And then you build a kernel regression model, to estimate how much gold is there, basically, and there, and everywhere else where it's white, okay? So the point is we have X, you know, 1 is, you know, latitude, and X2 is longitude, or something like that, longitude, and Y is the concentration of gold in that particular location, and you would like to, your test inputs are all locations where you haven't measured. Okay, so kriging is a kernel regression method that came from mining and geotechnical engineering, and it's basically using radial basis function kernels, and in the kernel regression framework that we just talked about. Pretty cool. Additionally, kernels allow us to think about some other stuff, right? So we've had this, you know, this ongoing discussion about data that doesn't look like, you know, real valued matrices, you know, English versus French sentences, right? One of the nice things is that the kernel trick allows us to fit regression models without actually explicitly constructing features, right? What we're really looking at are similarities, right? So we don't need to explicitly construct these features if we can compute the similarity between the objects. And we can interpret this kernel function, its output, as a similarity between objects I and J, right? So it gets really warpy to think about like what the spatial relationship of these is and what space you are in. But needless to say, you know, there are string kernels, image kernels, graph kernels, so on and so forth, okay? So what kernel functions can we use, right? So basically, a kernel has to correspond to an inner product in some space, and it's not easy to work with this, okay? There has to exist a mapping from X to some Z such that, you know, when you compute the kernel function, it has the same value as the inner product in this space. And it can be very hard. Massive amounts of research go into this, particularly in the late 90s, early 2000s. It can be very hard to show that a function satisfies this. It's a very, very complex problem. But like for continuous functions, there are constructivist definitions of how to build kernel functions through kernel function compositions. And David Duvenel at the University of Toronto has my favorite kernel composition workbook. It's in fact called the Kernel Cookbook, which is part of his thesis from University of Cambridge. Anyway, so besides L2 regularized least squares, where can we use kernels? Well, if we want to compute Euclidean distances in some high dimensional feature space, well, this looks like this, which we can transform into a kernelized operation, right? So long as we have a kernel function that produces these inner products, then we can do, you know, we can compute Euclidean distances using kernels, or kernelized versions of Euclidean distances, right? So that means all of our distance-based methods have kernelized versions. Kernel k-means, k-nearest neighbors, kernel clustering k-means, kernel density clustering, kernel hierarchical clustering, So, okay. It's sort of like physics, that's right. You know, go through Newtonian physics and then, yeah, then everything is just blown up. But in order to make it so that you can actually think about what's going on here, you have to understand what regularization is, and you have to understand what feature basis expansions are, you have to understand a whole lot of stuff, and then you get here and you say, okay, actually, you know, let's just use kernelized versions of everything, forget, you know, trying to do feature engineering. This is kind of like the you know, we've got linear models and linear regression and feature engineering and that sort of stuff, and then then this kernelized stuff took off, and they're extremely powerful general purpose methods that work even in the big data domain, and they took off before before deep neural networks did, right? So a kernel KNN godlike, is it a kernel KNN godlike then? I don't know what God is like at all, so I can't really answer that question directly, but you know, it's a model family to consider. Yeah. So if I come up with a weird polynomial basis that happens to work well for my regressor, well, I have to derive a kernel from my basis. It doesn't probably exist. So if you have a polynomial basis some weird polynomial basis, right? Use the Gaussian-RBF, right? It's basically or a polynomial kernel with high degree. Your weird polynomial basis is going to be a subset of those, right? And the regularization will, you know, pick out the correct subset for you. So you don't have to worry about it, right? That's kind of the point, right? You have now a very generic feature set, right? Infinite dimensional, you know, Taylor expansion, think Fourier transform, think blah, 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 blah. So would it be bad advice to just always try the Gaussian one? No, that's really not bad advice. It's usually what you start with. Actually, I think it's do you know, Payman, off the top of your head, matern 5/3, matern 5/2?
No.
What's the sort of like there is you know, it turns out that the Gaussian one is not the one that actually usually wins, because it suggests a smoothness that isn't actually really in real matern 5/2. I can't. There's the kernel that everybody uses that wins everything is matern. I bet if you type, I'm going to start typing matern 5. Yeah, matern 5/2. That's all you got to do. Matern space 5, and you type it in Google, and it'll talk about the matern kernel. And that's kind of the winner. It's super complicated algebraically. The maths related to it are completely ridiculous, and basically it suggests a different kind of smoothness. It makes a different smoothness assumption at like some order of derivative, whatever. So you can go down this rabbit hole as far as you want to. It's a deep rabbit hole. And amazingly, we have a new faculty member starting at UBC whose specialty is kernel methods, Dougal Sutherland. He's really interesting, so you should look him up. Okay. So there's a representer theorem basically that says that any L2 regularized linear model can be kernelized. In brief, basically, you can show that if your model or learning algorithm can be written in this way, then you can invoke a representer theorem, reparameterize in terms of basically reparameterize your solution vector in terms of some Z transpose U, basically just reparameterizing in terms of some weighting of the data, basically. And in that case, now you can basically build kernelized versions of everything that we've talked about in again with, you know, L2 regularization and whatever loss function. So we've got all kinds of loss functions that would sit here, right? What loss functions we talked about that sit here? Logistic, hinge, you were muted, whatever. So basically all of our logistic classification, or all of our linear classification models and the losses fit into this framework, so we can basically kernelize all of them, right? And the procedure is exactly the same as the linear regressor, right? That means we can do L2 regularized robust regression, derivative regression, logistic regression, hinge loss, support vector machines, so on and so forth. And it's close. This is as close as we get to real SVMs in this course with a particular implementation. You can reduce the prediction cost in SVMs to basically OMDT, and that's a big deal, right? So basically, you can, where M is the number of support vectors, right? So you don't have to actually, like, even though it's a non-parametric method and so on and so forth, because of the sparseness of the SVM solution, you can actually express prediction in terms of a very, very low cost operation. What do decision surfaces look like for these kinds of models? Well, here's linear logistic regression. If you're familiar with that, that's more of these loss functions that you then kernelize to the representer theorem, so on and so forth. There's kernel linear logistic regression. This is the dumb kernel where you do no op, no, it's the no op. But then if you do polynomial or RBF logistic regression, kernelized versions, then you transform decision surfaces pretty dramatically. So here's, our original, hyperplane, and now we've got really crazy hyperplanes where, that's this is a hyperplane in some very high dimensional space that when you project it back even has, holes in it, right? So it's pretty cool. Okay, I think that's all I can do today. The last bit is stochastic gradients, and we'll get into that starting Monday anyway. So cool, thanks for your time, and I can take questions until 5 or so. Thank you. When will the cat go? Has it been 5 days? Has it been 5 days?
It was 26, so not yet.
So we have to wait for 5 days. Right? The TAs in this course are wonderful, and they're they're on top of everything. We will see soon enough. Yes. It's going to be fun. We'll the beautiful thing is it's very easy to call out whomever overfit by cheating in some sort of a way. Test error brings all new meaning to the phrase test error, right? Everybody's watching the actual numbers. That's awesome. We'll see some. So yeah, Ramon, or is it Ramon Raymond? I forget. Raymond or Ramon?
It's Ramon.
Ramon, yes. Sounds better for me anyway. Is there a solution model? We have a solution model. I'm not sure that we'll distribute it. What we'll do is ask the best performers to release their code so you can see what they did. I think that's probably the best way to do it. Yeah, and it's not clear that we'll see the best model. We will see the best model on, yeah. Is the solution model good? Yeah, it's pretty good. Yeah. I mean, yeah, it's not down to like 5, 40, 50. I'm curious how people got, yeah, of course. How they got, 0 test error on the, on the training data, but we shall see. Okay. Cool. Thank you very much. Enjoy the weekend. Happy Halloween.